Okay, in this video, I wanted to walk you through a problem that's representative of what you might see on the online exam that's coming up for SMAC. Okay, so let's consider a system that has an input x, and this is just to remind you, x is a function of time, x of t, and it has an output y, and this system is described by an ordinary differential equation given below. Okay, so the first step is I want you to find the transfer function, and then we're going to look at the impulse response, do a pole zero diagram, find the step response, and then this is not clear, determine the final value of the system step response, I should say, using both a time domain approach and the final value theorem. Okay, so let's get started. I've already typed in the equation for the transfer function because, you know, I've done this a lot of times. I think you've done it when you've done your homework, and you can just write this down by inspection. All right, if you took the Laplace transform of this equation, every time you see a derivative, you add a power of s. So there would be s cubed y plus 10 s squared y plus 49 sy plus 100y is equal to 3sx plus 2x, where all these are the Laplace transform of the appropriate signal. Okay, and so when you do the rearranging, you get the denominator term, that's the coefficients in front of the y's, and you get the numerator term, that's the coefficients that are in front of the x's. Okay, so hopefully you follow that. So this is our transfer function, and so that solves part 1. Okay, for part 2, all right, we're wanting the impulse response of the system. So remember, the impulse response is the response of the system to an impulse. Okay, so x of t is a delta function, but the Laplace transform of x, capital X, is 1. I take the Laplace transform of an impulse, you get 1. All right, and so then y would be h times x, that's the convolution result we talked about, and then I just do an inverse Laplace transform of cap y. Okay, so I'm going to run that to get the answer, and here we are. This is an answer of, that gives me the impulse response. Okay, so I see there's a real exponential, and then there's this exponential that's multiplied by a sinusoid. Remember that video we talked about combinations of sines and cosines were reduced to a single sinusoid with a phase shift. So when I look at this, that's what I see. I see a single sinusoid with a phase shift, okay, that's multiplied by e to the minus 3t. Okay, so everything is well behaved here. The impulse response is not shooting up to infinity. You could graph that and look at it if you wanted. Okay, so that's part 2. So next what I want to do is go on and do part 3. Okay, in part 3 we're looking at the poles and the zeros. All right, so the zeros are pretty easy. I'm just going to go ahead and do this in MATLAB to show you a technique for finding poles and zeros in case it's more complicated. Okay, so you do num den of h to separate the numerator and denominator, and then if you want the poles, all right, it's just solve where the numerator is equal to 0. Okay, and if you want the zeros is solving where the numerator is equal to zeros. Okay, and then the poles are you solve where the denominator is equal to 0. Okay, and we rerun this. And we get a pole at minus 2/3. I say pole. 0 at minus 2/3. And a pole at minus 4 and negative 3, minus 4i, and minus 3 plus 4i. Remember, MATLAB uses I instead of J, so you can substitute a J in there. And we can do a diagram from that. I think that's pretty straightforward. I'm going to show you that. Okay. All right, so that's part 3 where we did a pole zero diagram. Next, we want to find the step response of the system. Okay, so let's go to part 4. Okay. Oops. Let's make it at the end of this. These are out of order, but you get the idea. This stuff needs to move at the end. It's confusing when you show it all in one. Okay. Let's get this all in the right order. Okay, so that's good for the first 3 parts. Now let's go to the 4th part. For the 4th part, we're trying to find the step response. Okay, so for the step response, we have the Laplace transform of a unit step, which is 1 over s. Okay, and from there, we know that y is equal to h times x. H is the transfer function, x is the input, and we can find the inverse Laplace transform of cap y. All right, so we'll run that, get those results. Okay, and we see from part 4, we have the impulse response. Okay, and we could have predicted the form of the impulse response because we know we have a pole we have poles at -4, -3, plus and minus 4j. And so we were expecting e to the minus 4t term. We were expecting a decaying term on this sinusoid of e to the minus 3. And we were expecting a frequency on the sinusoid part of 4 because of the plus and minus 4j. Okay, so that's matching what we expected. All right, so now we can move to part 5. All right, in part 5, you could take the limit at this point. Just look at the equation, write that equation down, and take the limit. So if you take the limit as t goes to infinity, you can tell, you know, the exponentials go away and you're left with just the constant term. I'm going to go ahead and do this in MATLAB though. I'm going to call this y final is equal to the limit of lowercase y. We're looking at the time domain. T is the variable. That's why I had to define that in the sims command here. Okay, and we're going to go to infinity. All right, so that's how you would do that in MATLAB. And when we run that, we get the final value of 1 over 50 as we expected. Okay, the other thing that I wanted you to notice is that you can use the final value theorem to look at the final value of a given output, provided that the system is stable, meaning that it has poles in the left half plane. We're going to talk a little bit more about that as we go through the course, but we have talked about it a little bit in one of the videos that was on Canvas. Okay, and so I can actually compute this in a different way. I can take the limit of s times y evaluated at s equals 0. Okay, so that's what all that means. I'm taking the limit of this function as s goes to 0. Okay, and so when I run that, I get yf2 giving me the same answer because all the terms in this decay properly is where the final value theorem will work. Okay, the final value theorem does not work if the function does not have a limit, like it's shooting off to infinity. It'll still give you an answer, but it gives you the wrong answer. Okay. All right, so that's an example of some stuff I'd like you to be able to do whenever we work together on our online exam next week.